Alright, so we now are going to see the final exercise of this section. Now this exercise is also about such series that we have been dealing with for some time now, that is a conditionally convergent series that is not absolutely convergent. In Riemann's theorem we have proved, although a part of the proof is still open means for us, because in the last part I have made a mistake. Okay, so unless you find what that mistake is, I am not going to go back to that. So that is a separate issue. But in Riemann's theorem, we saw that any such series can be rearranged to make it converge to any chosen real number. Here we are going to show that such a series can also be rearranged to make it diverge to plus infinity. Or if one wants to state it using limit superior and limit inferior, then these are also, we can show this also. We are not going to be worried about this thing though. We are just simply going to show that there exists such a bijection using which we can rearrange the series such that it diverges to plus infinity. In what sense? In the sense that the sequence of partial sums of this rearranged series will diverge to plus infinity in the usual sense. So let's see how this can be done. If one wants, one can also use Riemann's theorem, because that is available to us. After proving Riemann's theorem only, we are supposed to attempt this exercise. However, that is just simply a possibility. I don't see how Riemann's theorem can exactly be applied here. We are just going to do all the things from scratch. So this is how a solution can be thought of. So in the beginning itself, we are going to use our hypothesis, because it's given that the series is conditionally convergent but not absolutely convergent. So we can immediately use lemma 827, which comes before Riemann's theorem, and where we encountered those sets A plus and A minus, if you recall. So from that we have this, since summation an is conditionally convergent but not absolutely convergent, lemma 8 to 7 implies that the sets A plus and A minus are both infinite. We know what these sets are. A plus is the set of those indices n for which an is non-negative, and A minus consists of those indices n for which the corresponding an's are negative. So that means these are subsets of the set of natural numbers. And how exactly are we concluding that these two are infinite? Because in the statement of this lemma, it's given that these sums are not absolutely convergent. This sum and this sum. So neither A plus nor A minus can possibly be finite, because if they are finite, then there is no question of non-convergence. And that's how we are concluding that this must be infinite. So these are infinite subsets of the set of natural numbers. And we know that for such sets, we can find increasing bijections between each one of them and the set of natural numbers. So that's what we are next going to choose increasing bijections sigma from the set of natural numbers onto A plus and tau from the set of natural numbers onto A minus. Now we are going to again use this lemma in this way. Since by lemma 8 to 7, this sum A plus is not conditionally convergent, is not conditionally convergent. So not conditionally convergent means what? It just means that regardless of what bijection like this, for example, you choose between n and A plus and use that bijection to turn this sum into an ordinary series, that series is going to be divergent and it is independent of the bijection that you choose. That's what not being conditionally convergent means. Okay. So in particular, if we use sigma to turn this sum into a series, that series will also be divergent. The series summation A sigma of I is not convergent. Not convergent means divergent, of course, by definition. But it's not just simply a divergent series, it's a special kind of divergent series. Since an is non-negative for all n belonging to A plus. So if that is the case, then what do you think? What kind of divergence we will have here? Since all the terms involved, you see, all the sigma i's are after all elements in A plus, because sigma is a map from n to A plus. So all these terms are non-negative real numbers. And that's why the sequence of partial sums of this series is going to be a non-decreasing sequence. So when that type of sequence becomes divergent, it only diverges to plus infinity. Okay, it either, as you go down the sequence of partial sums, the successive terms either they stay the same or they increase. Now eventually if they just stop growing, then they will become convergent, but that is not the case. So they have to keep on growing and exceed every real number eventually. That's why it has to diverge to plus infinity, and this is the crucial fact that we are going to use. So because of all these things, summation A sigma of I where I varies from 0 to infinity, diverges to plus infinity. And if you want, you can refer that result here also. I mean, what will that be? It will be, I think, lemma 731 or something like that, where we deal with convergence or non-convergence of series of non-negative real numbers. So go back to that section, then you will understand what I am talking about. Okay, so now how can we use this fact? Let's see. We are now going to use this divergence to define a sequence of natural numbers. Recursively. We now define Ni recursively as follows. Okay, so that means first we have to define N naught, N0. N0 is defined to be the minimum of this set. It's going to look a little complicated, okay, but we will eventually understand what's going on. Let me first define it. Summation A sigma of j, where j varies from 0 to n, that is greater than minus a tau of 0. We will see afterwards why these things are being considered. So whatever it is just n naught. And then recursively, say you have already defined n naught, n1, n2 up to ni. Then next you define ni plus 1. Then ni plus 1 is again the minimum of such a set such that n is greater than the maximum of the previously defined ni's. That means where j lies in this range, and also simultaneously this sum, this finite sum, has to be greater than, now not minus a tau 0 but something else. Just give me a moment, okay? I want to see something. No, that's okay. So now this sum has to be greater than I plus 1 minus summation A tau of j, where j varies from 0 to I plus 1. What a messed up definition. It looks like that. I mean, suddenly out of nowhere we are considering these things, but things have been fine-tuned so that we ultimately get what we want. We will see. So let us now first see what this definition even means. Okay. So what we had here that we don't have here anymore we had this fact, no? A sigma of I, this series diverges to plus infinity. What it means is that if you give me any real number, no matter how large, say something, say R is any real number, positive, negative, it does not matter, preferably positive, just in order to show this divergence, but we can take negative also. Then there exists at least one partial sum in the sequence of partial sums of this series that will exceed this R. And if this continues to be the case for any chosen R, then then that sequence of partial sum diverges to plus infinity, and hence by definition the series also diverges to plus infinity. That is, if this R, there exists an n such that this partial sum exceeds R, then that's what diverging to plus infinity means. Okay. Now you look at this set. Forget about minimum for a moment, just look at the set. This set consists of all the natural numbers such that the corresponding partial sums, just like this one, exceeds this real number. I mean, after all, this minus a tau 0, whatever it may be, it's a real number, right? So this exceeds this. Now we know that because of this divergence, there is at least one such partial sum, and correspondingly at least one such n for which this will happen. There may be many such n's, but the fact is that since there is at least one such n, this set is a non-empty set, and it's a non-empty subset of n. So by the well-ordering principle, it will have a minimum, and that minimum has been defined to be n naught. So n naught exists and is unique. Okay. What about this one? This one also looks similar, but there are differences. Here the set is the set of all natural numbers for which, now again you see, here also we have the partial sum corresponding to n. Here also we have that same thing, but now it has to exceed this thing. Okay. And because I is something given, I mean I will be given, so this is a chosen real number, this entire thing. So for some n, this sum will also exceed this, and there may be multiple, actually there will be many, infinitely many such n's, but at the same time we also demand that the n that we are going to choose has to simultaneously exceed the previous ni's that have already been defined before defining this. The fact that such n exists again comes from this. Why? Because actually not just one such n exists, but infinitely many such n's exist for which these partial sums will exceed this. So from among infinitely many such n, of course you can choose one that exceeds the previously defined ni's, because the previously defined ni's are finite in number. That's why. So this set is also non-empty and a subset of n. So by the well-ordering principle, it also has a unique minimum, and that minimum is ni plus 1. And now all of these things we are just simply going to justify by writing one line. Note that the above definition makes sense because summation a sigma of I, as I varies from 0 to infinity, diverges to plus infinity. So there is no problem with this definition. Ni is a well-defined sequence of natural numbers. Now what are we going to do with this Ni though? So that is coming next. But before that, we are going to notice one thing about these Ni's, which I am just simply going to mention. If one wants, one can prove by induction. It's absolutely straightforward. Okay, it just almost comes directly from the definition itself. Note that Ni is strictly less than Ni plus 1 for all natural numbers I. That is because, you see, Ni plus 1 is the minimum of this set. That means it's after all an element of this set, and being an element of this set, you can put Ni plus 1 here. So Ni plus 1 is greater than all the previous Nj's, and among those Nj's, Ni is one such. So this fact we can systematically prove by induction, or it is almost obvious. This for all n, proved by induction on I. Okay, so now we, just like Ni, now we are going to define something else. We are going to define another sequence. We now define a sequence Fi using this sequence Ni, of course. That also is going to be well, not recursively, but the definition we will see. Let's see what it is. We now define Fi as follows. Okay. Now the definition of Fi would use the sigma values as well as the tau values. Now the first part of this definition goes like this. For you can of course see that I will be a natural number, and we need to just define Fi for each natural number I. Now if your input I lies in this region, if it lies between 0 and n naught inclusive, then Fi is defined to be equal to just sigma of I. That's it, nothing else. But then what about those i's that exceed n naught? I is greater than n naught, say, then what happens? Next, let I be greater than n naught. Then there exists a unique natural number k such that, yeah, this part is a little confusing. I don't want to make a mistake. Nk plus k plus 1 is less than or equal to I, which is less than or equal to nk plus 1 plus k plus 1. But this, looking at this last sentence, you may be wondering why, how is there a unique natural number k for which this happens? For that, you notice this. Since, so I is greater than n naught, right? And these are natural numbers. So I has to be greater than or equal to n naught plus 1. It's something that we proved way back when we were constructing the system of natural numbers. If this inequality is true, then this is true, and conversely, they are equivalent to each other. And if you notice carefully, this n0 plus 1 has the form of this number, n0 plus 0 plus 1. And because of this, the set that I am going to write next, that will have some property. So the set is this. Hence, the set, this set, the set of all natural numbers beta such that beta has this form, n alpha plus 1 for some natural number alpha, and at the same time beta is less than or equal to I. This set is non-empty and finite. Okay, why is it non-empty and finite? That's because you see that you are at least getting n0 plus 0 plus 1 as an element in this set. How? Because you can choose this value of beta. It has the form that beta should have, n0 plus 0 plus 1. So in this case alpha is 0. But at the same time, this requirement is also true for this particular number. So you have got at least this element in this set. But at the same time, because we are considering only natural numbers less than or equal to I of a special form. So the set of all natural numbers less than or equal to I is a finite set. So this is a subset of even that set. So it is also finite. So this is a non-empty finite set. Let nk plus k plus 1 be the largest element of this set. Because it's a non-empty finite set, it will have a largest element. And in order to have a largest element, we need finiteness. Okay, if we just simply have non-emptiness, then there exists a smallest element by the well ordering principle, but not necessarily largest. But this one will have a largest. Okay, and why is this largest element of this form? Because that's the form the elements in this set have. Okay. Then, since this is after all an element in this set, this will be less than or equal to I. But if you consider nk plus 1, say nk plus 1 plus k plus 2, You look at this number also has the form that the elements of this set have, where in place of k we have taken k plus 1. So here you have k plus 1 plus 1, so k plus 2. But this number of course is not equal to this number, obviously, for two reasons. One is that, okay, let's see why that is true. You may argue that no, it may be the case that this number is actually equal to this number. Can that happen? Suppose you argue that you have this, but then after some cancellation, what we will have, nk is equal to nk plus 1 plus 1. But this is simply just impossible, because you remember after defining the sequence ni, we concluded that it's a strictly increasing sequence. Ni plus 1 is greater than ni. So nk itself is less than nk plus 1. So how can nk be equal to nk plus 1 plus 1? So that's why that is not possible. So that means in spite of being of this form, this number cannot be in this set because it exceeds the maximum number in this set. Okay, and that's why it cannot be less than or equal to I, because otherwise, since it has the form to be in this set and also it is less than or equal to I, it will belong to this set, contradicting the maximality of this number. So that's why it cannot be less than or equal to I, and that is why it has to be strictly greater than I, right? But then what is the consequence of all these things? Since we are after all dealing with natural numbers, in place of these inequalities, you can write these inequalities also. If you subtract 1 from this, then it will either be equal to I or it will still stay greater than I. So that's why you have this, and which is what we have written here. So this is the explanation for this. Okay, fine. So if our I lies in this range, that is if it exceeds n naught, then there exists a unicorn, and should I write something about this? In this discussion, it's of course obvious that k is unique. So if you want, you can just simply write that afterwards, but I'm not going to write that, okay? So that's why there exists a unique k for which I lies between these two numbers, but now what? Now for this type of I also we need to define fi. So that's what we are going to now do. We now define. So you see, there are two cases that we will consider. In one case, I is equal to this, and in the other case, I is greater than this, but of course satisfies these inequalities. So the first case is what happens to fi if I is equal to this. In that case, what is fi according to us? That means f nk plus k plus 1, this we are going to define as simply tau of k. Okay, that's what f of this means. And f of I, if I is greater than this but less than or equal to this, then for that kind of I, fi is defined to be sigma of I minus k minus 1. If I is satisfying these inequalities, okay. So don't you think that we have actually defined fi for all natural numbers I? We have, and this is why if I lies in this range, then we have defined fi to be just sigma of I. And if I exceeds n naught, then for such an I there exists a unique integer, unique natural number k for which all these things happen. And there also, if I takes this value, then the corresponding f is tau of k. However, if I does not take that value, then the corresponding fi is this. Okay, so that means we have defined fi for all natural numbers I. And because these definitions have used just either sigma or tau, which themselves are well-defined functions, so fi is also a well-defined function from n to n, and that is it's a well-defined sequence. We can mention that since sigma comma tau are well-defined, so is the sequence fi. Now, a sequence is, the kind of sequence we have defined where the terms are also natural numbers is after all just a function, right? We thus have a function f from n to n such that f of I is equal to fi. So this is just another way of writing this sequence as a function. Okay. Now this is the function that the exercise is seeking. That is, this is the bijection that will rearrange the series so that it will diverge to infinity. But we have just simply got the function at this stage. Now we have to show that it's a bijection. We now claim that f is a bijection. So that means f has, we have to prove that f is one-to-one and onto injective and surjective both. Now it's very easy, almost instantaneous to conclude that f is injective. That is because, have you seen how f has been defined? Each value of f is either a sigma value, in the range between 0 and n naught also it's just ordinary sigma I, and elsewhere it looks like this. After all, these are sigma values and some other values are tau values, and these two things are themselves injective. Why? From where are we getting that? So that is because we have chosen sigma and tau themselves to be bijections, and not just that, increasing bijections. So sigma and tau are both injective, but there is another point here that will help us. Why? Because you see, sigma maps n into a plus, whereas tau maps n into a minus. And we already know from lemma 8 to 7 that these two are disjoint sets. So that is why the function looks somewhat like this. Here you have n, here you have a plus, and here you have a minus. And the f of course runs from n to the union of these two, which is also after all n, that also we know. Some of the f values are in a plus and some of them will be in a minus, that is those where we are having tau in the definition of f. Now the part that maps the natural numbers to the elements in a plus, that part is injective because it is after all sigma values, and this part also is individually injective because these are the tau values, and these two sets are disjoint. So no possibility of having any many to one kind of behavior that can possibly arise, that would have arisen had these two things not been disjoint. But that is not there, so that's why there is no chance of having two different inputs that will give you the same output. See, if those two different inputs fall under the sigma category, then of course the outputs are also different because sigma is injective. If they fall under this type of conditions, then also they have different outputs because the function tau is injective. But the possibility that you may have had that some sigma definition and some tau definition actually give you the same output, that is also not possible because the sigma definitions are going to map into a plus and the tau cases are going to be mapped here. So no question of having the same output. So that's why we are now going to write, since a plus intersection a minus is empty, sigma maps n into a plus, tau maps n into a minus, and sigma comma tau are both injective. F is also injective. Okay, so that way F is injective. Next comes surjectivity. Next, so for surjectivity we will have to choose again a natural number and show that that is the output under F for some input. Now since we know that n is the union of a plus and a minus, that chosen natural number will either lie in a plus or in a minus, but not in both because of this disjointness. So let us first consider the case where that number lies in a plus, say. So let R1 belong to a plus. Now we know that sigma is surjective because after all it's a bijection. Since sigma is surjective, R1 is equal to sigma of rho 1 for some natural number rho 1 Okay, but now what kind of input can we use to have this as an F image? For that though, we have to consider two cases. If this rho 1 lies in this region in N, then of course R1 is equal to sigma of rho 1, but that is just simply equal to f of rho 1, because for this kind of inputs f is just sigma. Now assume that rho 1 is greater than n naught, then there exists an S in N such that Ns plus 1, is that what we have here? Yes, Ns plus 1 is less than or equal to rho 1, that is less than or equal to Ns plus 1. I am not again going to explain how we are having this. You just go back to the definition of f. Okay, there you will see that such an S exists. We have already gone through it once, right? Then in that case R1 is just sigma of rho 1, but that is equal to f of n rho 1 plus rho 1 plus 1. Well, if you still want an explanation, it is like what we saw before, but not exactly what we saw before. You see this thing, rho 1 is greater than n naught. So obviously rho 1 will be greater than or equal to n naught plus 1. So now in place of 0, if you think of S, then you are looking at Ns plus S plus 1. That kind of number, if you think of it. So that means Ns plus S plus 1 you can have, that is less than or equal to rho 1. Then the next one, Ns plus 1 plus S plus 2 will be strictly greater than rho 1, and in this part the arguments are just like those arguments that we already have seen. And then if you just simply subtract 1 from here, then you have the possibility of equality. Okay. No, but then exactly I am not getting this thing, no? No, exactly I am not getting the same thing. So what was the argument here? So it's okay, so it's a little ironic. I told you that we can similarly get this, but I am myself not getting it. There exists an S belonging to N such that this, then R1 is equal to this. Okay, just for the moment, assume that we have these inequalities, and let's see how we are getting this though. If you have this inequality and then you add S throughout, then you will have this, right? And then if you go back to the definition of Fi or F, then what are you getting? No, oh, okay. That's why I got confused. This is not n row 1. This is row 1 plus S plus 1. Okay. So that means if you add another 1 here, that means here you will have 2 and here you will have 1. And then you go back to the definition of F suffix I in that other case where your thing that I exceeds n naught, and I mean in that case we defined Fi in two different ways, right? For the smallest possible value, that is nk plus k plus 1, we defined F at that point to be tau of k, and it is that other case under which this falls. So that's why F of this value is going to be equal to, you imagine that definition. There we had Fi is equal to sigma of I minus k minus 1, right? Here in place of k you are having S. So F of this will be sigma of this minus S minus 1, and that's why you will have sigma of rho 1. So this part, once you have these inequalities, it is understood how this is coming. However, what is still not clear to me also is how we are getting these inequalities. Let me just think about it for just 1 minute. And if I don't get it, I will just have to leave it like this, leave it to you, and I will also think about it, and then I will come back with an explanation. So what is happening here is that rho 1 is greater than n naught. So if we go just like we went there, according to that line of argument, then there we considered that set, no? Beta such that this for some alpha and this was less than or equal to I. In this case, instead of I we have rho 1. Okay. Is that what we are, is this the thing that is going to give us this though? That's the question. Okay, let's just leave it like this itself. So this part is not understood. How this is coming? Just a few hours ago I understood how, but I have forgotten. Okay, so maybe I will write it in the comment after uploading it after some time. So for now, this part is not understood, but let's just go ahead. So we now have this. So that means if our R1 is coming from A plus, then R1 appears, no matter what the case is, as an output under F for some input. Next, let R2 belong to A minus. This one is easier because these are just some technical things. No, just one argument. If we forget how it comes, then that's just it. Since tau is surjective, we have R2 is equal to tau rho 2 for some natural number rho 2, but the definition of F where tau is used is very straightforward. But then R2 is equal to tau of rho 2, that is equal to F of, this is where we will have that thing, n rho 2 plus rho 2 plus 1. Okay, so it is that kind of number, n alpha plus 1, at which the F value is tau of something, and that something is that alpha, or nk plus k plus 1 tau of k. Hence, so that's it. If our chosen number is coming from A plus, then also it's an output. If it's coming from A minus, then also it's an output under the function f. Hence, f is surjective. Okay, so we have now shown that f is both injective and surjective, so it's a bijection. Okay, now we deliver the final blow. Now, from the construction of Ni and the definition of fi and hence the function f, we have these next things. Okay, so now what we concentrate on is this. F of j, where j varies from 0 to ni plus I plus 1. If you are thinking what I is some natural number, that is your choice. Okay, I is any natural number, that is your choice. For that kind of I, let's look at what this sum is and what, this is the, you can immediately see one thing. It is one partial sum for the rearranged series. Because we have now proved that f is a bijection, we can use it to rearrange our original series, then the rearranged series will look like this. Now we want to show that the terms of the sequence of partial sums of this series exceed any chosen number. Now it's also enough to show that these terms exceed any natural numbers, because the natural numbers themselves are unbounded from above. So if the partial sums exceed all the natural numbers, any natural number eventually, then that's equivalent to exceeding all the real numbers also. So now what we want to show is that this particular partial sum exceeds I. So that's why I said I is your choice from N, the set of natural numbers. Is that so? Let's see. We have done so much with all these symbols. Let's see if that pays off. We are now going to divide this sum into other sums. Carefully, according to how we have defined f. So first our j we keep between 0 and n naught, okay, and then the next term of course is f of n naught plus 1, that we keep separately, okay, just simply as one term. Then we write another sum where now j starts from the next natural number, that is n naught plus 2, and we go till n1 plus 1, and then we keep one term, that is the next term, separately. So the next term is going to be n1 plus 2. Let's write two more like this. Summation a f of j. Here j will vary from n1 plus 3, and we are going to stop at n2 plus 2, and then the next one we are going to keep separately, which will be n2 plus 3, and it goes like this. Like this, if one goes, then one would eventually reach this. If whatever you have here, here you have one more than that. You see, 0, 1, 1, 2, 2, 3. So eventually I would have one n I minus 1 also, because we have all these things, n I plus 1. So n I minus 1 will be reached at some point, but then I, because one more, plus then a sum, and that sum is a f of j, where j varies from, now the next index value have to be written here, n I minus 1 plus I plus 1, okay. You can see if you have made any mistake by looking at the difference. The difference between I minus 1 and I plus 1 is 2. Do we have that kind of difference here? I mean, the first one is of course 0. See, 0, 2, 1, 3. Okay, and how far shall we go? We will go till n I plus I, because we are going till that kind of thing. You see, n0 plus 0, whatever you have here as suffix, that you have with a plus sign, n0 plus 0, n1 plus 1, n2 plus 2, and so on. And now we have only one more value of j left to us, that is ni plus I plus 1. So we are next going to write that separately, ni plus I plus 1. Okay. Now if you go back to the definition of f, the function f itself, you will see that these sums have the kind of j where the definition of f uses sigma, and these single terms correspond to those f values that have been defined using tau. More precisely, in this sum, f of j is just sigma of j, because here j lies between 0 and n0. Sigma of j. What about this one? This is just a tau of 0. Is it really? If so, how? You see, f of n0 plus 1 is equal to f of n0 plus 0 plus 1. Nk plus k plus 1. We have defined f to be, for that kind of input, just tau of k, but in this case k is 0, so tau of 0. So that's why that. Plus, so now that we have understood this, we can keep on going like this. What will happen to this sum? The limits, of course, will stay the same. So let's write them first. Here j varies from n0 plus 2 to n1 plus 1. And now f of j, okay, for this kind of j, you can see from the limits we are going to figure out what fj is. Here it will be j minus 1, because do you see what type of numbers we have here? J is greater than or equal to n0 plus 0 plus 2 and less than or equal to n1 plus 0 plus 1. So the k that you have here is 0. And how have we defined f for that kind of thing? There f has been defined to be sigma of j minus, j means the point where you are defining the function, sigma of j minus k minus 1, but k is 0 here, so j minus 1, right? And this one, the next one, n1 plus 1 plus 1, here k is 1, so tau of 1, plus, let's next see this one. This one, if you go just like that, you will see that it becomes j minus 2, and here j is varying from n1 plus 3 to n2 plus 2, then plus a tau of 2, because n2 plus 2 plus 1, and proceeding like this. Plus, okay, what will happen to that one? A tau, what will it be? N I minus 1 plus I minus 1 plus 1. So here k is I minus 1 plus summation A sigma. Okay, so now what will happen? You can take your cue from these signs. When you have 0 here, you are subtracting 0. When you have 1 here, you are subtracting 1. 2, you are subtracting 2. So what is it that you have here? I. So that means you will be subtracting I. From what? From j. And In this case, j varies from n I minus 1 plus I plus 1. There is a very high chance of making mistakes. Okay, so you have to be extra careful. And finally, this. Here, the k value is I, so a tau I. Now, still there is more work. These sums themselves can still be written a little more nicely, like this. And now we are going to write these sums together and write the rest of the a where the suffixes involve tau together. So the first sum is just this a sigma of j. Now in the second sum, you see, if you put the smallest value of j, that is n naught plus 2, then ultimately what does it become? It becomes n naught plus 1. And if you put the largest value, what is it that you get? n1 plus 1 minus 1, that means n1. So can I not write this sum slightly differently like this? A sigma of j itself I am writing, but since I want to have n naught plus 1 here, so now instead of not starting from n naught plus 2, I start my j from n naught plus 1, and here I will have n1. So now I have just simply this. Okay. You can think of this change of appearance in terms of a different j also. I mean, you do not call it j, but you call it something else, some other index. You get my point. Plus, then what happened to this sum? Similarly, if I just simply write j here, what we did, we subtracted 1. Here we will subtract 2 from this. From here also we will subtract 2. So here, now the new j starts from n1 plus 1 and stops at n2. Plus, what is going to happen to this? We are not going to look there, but here we have to subtract I from the lower limit as well as the upper limit and add I to this. So actually, essentially what we are doing is we are using one of the properties of finite series. You go back to those properties, you will see what I am talking about here. So that means here again sigma of j, and our new j will start from n I minus 1 plus 1 and it will go till n I. Okay, and that's just it. And now if you write the rest of the things, then that itself is also a sum, that is a tau of I, where I varies from 0. Oh, sorry, we cannot use I now, because I is not a variable here. We have to use j because it goes like this. Okay, now do you see what is happening? All the sums that have been written first can now be written as a single sum, because nicely wherever this one stops, from there the next sum picks up things. Where this one is stopping, the next sum is picking things up from there, and it continues like that. So all these sums ultimately become A sigma of j, where j varies from 0 to ni, a continuous uninterrupted sum, plus summation a tau j and this thing is greater than I, since now do you see why we define those ni's like that? In fact, in the definition of ni is the minimum of the set of those n's such that if you put that n here, then that exceeds this number. And ni being an element of that set will satisfy this inequality. And from this inequality we have this. So that means AF of j ni plus I plus 1 is greater than I. Oh, we haven't said what I is now. I.e. this for any I belonging to the set of natural numbers, and this proves that the partial sums exceed any given natural number. At least one partial sum exceeds. You give another natural number, another partial sum exceeds. So the rearranged series must diverge to plus infinity. Thus if you find my use of I here confusing, I can write j also. Diverges to plus infinity, and that's what we wanted to show. Okay, so this completes the solution, but still it's a little incomplete because of that those inequalities, right? I don't know why suddenly I forgot how they are true, but we will have an explanation anyway. So I am stopping the video here itself. I don't know how long it has been. Our next upload is this Tuesday, of course, and this Tuesday we are going to go back to group theory from Herstein. So see you on Tuesday with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.